Alright, I'm going to take a brief moment to talk about perpendicular bisectors and equidistant points. We've dealt with a bunch of problems where we're trying to find a set of points that are all equidistant from two given original points. And by equidistant we mean it's the same distance to either point. So I'm finding, so given some location here, some point A, and over here some point B, I'm trying to find 1, 2, 3. I picked two bad points, didn't I? I don't want it to be that way. Sorry. We'll do A and B down here. Okay. So I've got my A and B, and I want to find all the different places that are the same distance from A as they are from B. Let me take a look here. One such point would be right in the middle. That's the midpoint. Okay. Or I could go like straight up. You notice here, over 1 over 3 up 1, or down to B over 3 up 1. So if I did the Pythagorean theorem and I calculated those two distances from that point to A and that point to B, I'd get the same thing. I'll go up a little further. Here I have 2 down 2 over 3, or down 2 over 3 in the other direction. And become same distance from here to A as it is to B. And you can kind of see, I'm creating like a whole series of isosceles triangles when I draw in these triangles to do Pythagorean theorem. And I'm going to have a whole bunch of other points up here and down here. And in fact, there's this whole line of points that are the same distance from A as they are from B. It's not just the points that are on the grid too. It could be like some point part way in between two grid lines. So there's a couple of things about this this line here. One, because the midpoint is on it, right? It cuts the segment that connects A and B in half. Right? And that's what's known as a bisector. Right? So that's what makes it a bisector. Bi means to sect, like dissect, cut up. Bisect means to cut in two equal sized pieces. So this line of points cuts through the midpoint, so it's a bisector. Also, it is perpendicular to the original. So notice the original segment was horizontal, and the new line here is vertical, so it's perpendicular. It meets at right angles. So it's the perpendicular bisector. You can find that same point even if we don't pick two points that are perfectly horizontally across from each other. I could go, for example, here, down here, if I pick my A and B, I'm going to connect them with a little segment here. All the points that are the same distance from A as they are from B. Well, there's the midpoint. That's the first one. And I could go up here. Notice that's up 3 over 1. To A, it's over 3 down 1. So if I were to do Pythagorean theorem calculation to go to either A or B, I would end up with the same distance. Up here, well, this is straight down 4 or straight over 4, so same distance to A and B. Out here, it's up 1, 2, 3, 4, 5, and over 1. And here it's 1, 2, 3, 4, 5, and down 1. So again, if I were doing Pythagorean theorem, these distances to B will be the same as these distances to A. And you can see how this is shaping up. We're shaping up to have that same line. And if you kind of look at this one's going, the line is going up at a 45-degree angle. The segment's going down at a 45-degree angle. Again, they're perpendicular, and it cuts through that midpoint because the midpoint is one point that's the same distance to either end. So again, we get that perpendicular bisector. We can even do it with, I'm going to draw here. I'm going to tilt my A and B a little differently. Okay, so let's see. So I'll find all these points again. So there's the midpoint. That's the first one. Let's see, here's another one here. Up 3 over 1. Up 1 over 3. So same distance. Okay. So here's another one here. This is straight up 1, 2, 3, 4, 5. And from A to that point is 1, 2, 3, 1, 2, 3, 4. So if I were traveling up and, or if I did my Pythagorean theorem, 3 squared plus 4 squared is 5 squared. So the distance from A up to that point is 5. If you recall, it's that 3, 4, 5 triangle. Okay. So there's another one up here. This is 1, 2, 3, 4, 5, 6, 7, and over 1. And 7 squared plus 1 squared is 49 plus 1. You get square root of 50. And from A, it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I have 5 squared plus 5 squared, which is 25 and 25. So again, we end up with square root of 50 when we do our end calculation. And I can find some more points. Here's 1, here's 1, here's 1. And again, it's that line of points. Again, it's perpendicular, meets at a right angle, and cuts through the midpoint of that original segment. So it's a bisector, perpendicular bisector. Now you might ask yourself, how am I finding all those points? It just seems to be magical. Well, it's not actually magical. Let's take a look at how I'm finding all those points. So, given my original segment, let's see, AB. Now I'm going to go ahead and I'm going to connect it with A. There we go. And I'm going to look here and notice from A to B, I'm looking at the slope. And the slope is over 3, down 1, over 3, down 1. So it's over 3, down 1 pattern. And so we've got slope is rise, which really technically should be called delta y. That's your change in y. It's your up, down change, rise, over run. So, yeah, I know people say rise over run, but delta y and delta x are a little more mathematically accurate. It just means change in y, so that's how far up or down. And delta x just means change in x, so how far left or right. So from A to B, we make, well, we could do it as, down 2. So that's negative 2 because you're going down. And forward 6, or we could simplify that fraction to negative 1 over 3. And when you're trying to draw a perpendicular line, I need to take that slope and flip it upside down and change its sign. So 1/3 becomes 3 over 1, or just 3. So my slope needs to be 3, or 3 over 1. So that's up 3, forward 1. Now I'm starting from the midpoint, which is halfway between the 2 points, because it's a perpendicular bisector. So I start in the middle, and I go up 3, over 1, up 3, over 1. Or I'm going to go backwards, down 3, back 1, down 3, back 1. And then I can connect them with a line. And this is my perpendicular bisector. Remember, every point in the perpendicular bisector is the same distance from A as it is from B. Let's do another one. Say I had here, let's see, right here, A and B. So I connect them. I notice from A to B, there's an over 2, down 1, over 2, down 1 pattern. So our slope, I'll call it M here, is negative 1 over 2. So I'm just going to switch that up and change the sign and make it 2 over 1. That's negative reciprocal. So from the midpoint, 2 over 1, I go up 2, forward 1, up 2, forward 1, up 2, forward 1. And going back, down, back down, back down. We're just following, making the pattern in reverse. Okay. Here's one that's a little trickier. I'll do here and here. Okay. Oop, not space there. So when I connect the two here, I notice I have an up 3 over 2, up 3 over 2 pattern. So our slope from A to B is 3 over 2. So I need to switch it upside down, make it 2 over 3, and then change its sign. Make it negative. So from the midpoint, I need to go down 2, forward 3. So down 2, forward 3, down 2, forward 3. Back 3, up 1, back 3, 1. And there we go. There's our right angle. And it cuts to the midpoint, so it's right angle perpendicular, cuts to the midpoint, a bisector. So I would encourage you to like try some of these on your own. Yeah. And if things go wrong, you should be able to eyeball it and see, that doesn't look perpendicular, or it's not quite a bisector, or something along those lines.